So, in this lecture we will see what are the solution processes of various other type of ordinary differential equations and what kind of problems we may face. You see this problem now, y double dash t plus y dash t equals t with y 1 equals 1, y dash 1 equals 0. So, if you see here your problem is y double dash t plus y dash t equals t, and what is the conditions are given, y 1 equals 1 and y dash 1 equals 0. Please note this, that in the earlier problem we were obtaining the conditions at t equals 0, but here you have obtained the solution, obtained the condition at t equals 1. But you know, whenever I am finding out the Laplace transform of y dash or y double dash, always it will involve y 0 or y dash 0. So, I do not know the value of y 0 and y dash 0, but I know the value of y 1 and y dash 1. So, I may face this type of problems also. So, whenever I am facing this type of problem, that the value or initial or final value are not given at t equal, value of y or y dash or like that is not provided at t equals 0, then I can make the change of parameter, that is I can substitute t by some other parameter in such a fashion that the conditions I can obtain at some other variable equals new variable, that is equals 0. So, if I substitute say t equals tau plus 1, suppose if I substitute t equals tau plus 1, so that your tau will be t minus 1. So, at t equals 1 your tau will be 0, at t equals 1 your tau will become 0. So, once I am getting this, then these conditions also will be changing and we will obtain the condition about value of y dash y at tau equals 1, at tau equals 0, not at t equals t. So, whenever I am taking t equals tau plus 1 and y t equals say a new function y bar tau, because y t now will be a function of t. So, I am mentioning it as y bar. So, y t equals y bar t, if I put, then what will be y bar 0? Y bar 0 will be 1, because as I told you at t equals 1 your tau will be 0 and your y bar dash 0 will be equals to 0. And your problem is now transformed to y bar double dash tau plus, because there will be no change, y bar dash tau, this is equals, only t will be changed to tau plus 1. So, you see you had the original problem this thing, but since the conditions are not given here at t equals 0, but at t equals 1. So, I am changing the parameter t, I am using a new parameter tau such that t equals tau plus 1 and y t equals y bar tau. So, that my conditions are now changed to y bar 0 equals 1 and y bar dash 0 equals 0, and the differential ordinary differential equation changed to y bar double dash tau plus y bar dash tau equals tau plus 1. So, if I can find the solution of this, then by back substitution I can obtain the value of the y t also from y bar tau. So, let us try to find out the solution of the converted ordinary differential equation. So, if required, the original ODE can be converted into some transformed into some other ODE like this. So, now you use the proper form. You take the Laplace transform on both sides of this. So, that Laplace transform of y bar dash tau equals Laplace transform of tau plus 1, and Laplace transform of y double bar, you know it already, s square Laplace transform of y bar tau minus s y bar 0 minus y bar dash 0 plus s into Laplace transform of y bar tau. This is y dash. So, one more term will come minus y bar 0 and Laplace transform of tau plus 1, this will be 1 by s square plus 1 by s. So, you are obtaining this thing 1 by s square plus s. Now, substitute the value of y bar 0, y bar dash 0. If you substitute the values of this, which you know as y bar 0 is 1, y bar dash 0 is 0. So, on this equation by substituting, I will obtain this thing s square into Laplace transform of y bar tau minus s plus s into Laplace transform of y bar tau minus 1. This is equals 1 by s plus 1 plus s by s square. This will be, let me write it clearly, 1 plus s by s square. This I am getting. So, from here I can now find out Laplace transform of y bar tau. Laplace transform of y bar tau, this I can write down 1 plus s by s, s square will come plus s plus 1 into 1 by s into s plus 1. And from here I can calculate this one. If I simplify this, I will obtain simply 1 by s cube plus 1 by s. So, that y bar tau, now you can write down y bar tau, this is equals to Laplace inverse of 1 by s cube plus Laplace inverse of 1 by s. And once I am getting this y bar tau, this equals, you can write down 1 by s cube. So, tau square by 2, this is equals to plus 1. So, y bar tau, you are getting your tau square by 2 plus 1. So, from here I can obtain what is y t, because you know t equals tau minus 1 or tau plus t plus 1 equals tau. So, substitute by this, that is t minus 1 whole square by 2 plus 1. This you are obtaining as solution. So, y t equals t minus 1 whole square by 2 plus 1 is the solution of your problem. So, this is another kind of problem where we are just getting this one, where we are trying to find out the solution by changing the parameter t to some suitable other parameters. Let us see, just quickly let us see this one. So, by substituting t equals tau plus 1, I am changing the parameter, then I am getting the initial condition in terms of y bar 0 equals 1, y bar dash 0 equals 0. So, that your original problem is transformed into the other ODE, y bar double dash tau plus y bar dash tau equals tau plus 1. You take the Laplace transform now, follow the normal process as we have done earlier, and you get 1 by s plus s square. From here Laplace transform of y bar tau we can obtain, and directly by simplification Laplace transform of y bar tau is 1 by s cube plus 1 by s. So, that y bar tau is tau square by 2 plus 1, and so y tau will be by substituting tau by t plus 1. So, that t is tau minus 1. So, I am substituting that one. So, it will be tau plus 1 basically, because I assume that t equals tau plus 1. So, here it will be t equals tau plus 1. So, that your tau will be replaced by t minus 1 whole square by 2, and you will obtain the result as this one. Let us see another similar type of problem. Here also the condition is provided at t equals 1. So, I have to make the substitution over here. I am substituting t equals again tau plus 1 and y t equals y bar tau. So that your conditions at y and y bar will be changed at tau equals 0. So, y bar 0 is 1, y bar dash 0, this is equals minus 1. And your original problem is now changed to y bar double dash tau plus twice y bar dash tau plus y bar tau. This is equals 2 e power minus tau. So, your original equation is transformed to this. Now, you take the Laplace transform as usual on both sides of the given equation. So, that Laplace transform of y bar double dash tau plus 2 into Laplace transform of y bar dash tau plus Laplace transform of y bar tau. You are getting this, and Laplace transform of 2 e power minus tau. So, Laplace transform of y double bar, this is equals to s square into Laplace transform of y bar tau minus s y bar 0 minus y bar dash 0 plus twice s Laplace transform of y bar tau minus 2 y bar 0. This term is coming. For this Laplace transform of y bar dash tau, this term is coming minus 2 y bar 0 plus this term will come plus Laplace transform of y bar tau. This is equals to, for this the value will be Laplace transform of this is e power minus tau will be 2 by s plus 1. Now, substitute here the values of y bar dash, then you will obtain an equation of the form like this. Laplace transform of y bar tau, I am just skipping this here, you will obtain something like this 2 by s plus 1 plus s plus 1 into 1 by s square plus twice s plus 1. You will obtain this thing. Laplace transform of y bar tau, you will obtain this one. So, that if I simplify this, I will obtain Laplace transform of y bar tau, Laplace transform of y bar tau, this is equals 2 by s plus 1 whole cube plus 1 by s plus 1 I will obtain. So, y bar tau, now you can tell y bar tau, this is equals Laplace inverse of 2 by s plus 1 whole cube plus Laplace inverse of 1 by s plus 1, Laplace inverse of 1 by s plus 1, and these two are known to me. Y bar tau equals this, I can write down this s plus 1 also I can break it. So, that e power s plus 1 is there, e power minus tau, Laplace inverse of 2 by s cube I can write down simply, s plus 1 can be replaced, e power minus tau will come plus e power this s plus 1 also I can replace, e power minus 1 Laplace inverse of 1 by s. So, that I can tell that here values are e power minus tau into tau square 2 by s cube plus e power minus tau into 1. 1 by s for the function is 1, for Laplace transform of 1 is 1 by s. So, once I obtain the y tau, then I can find the value of y t. What I have assumed, t equals tau plus 1, t equals tau plus 1. So, that t will be t equals tau plus 1 since we have assumed. So, your tau will be t minus 1. So, minus t minus e power minus t minus 1 into t minus 1 whole square plus 1. You will obtain the result as this one. So, you see we are changing the parameter, and by changing the parameter we are bringing the condition into some format where we are getting ultimately y value of y 0 and y bar 0. So, this is one type of solution of ODE. So, we have done two type of solutions. One type is basically when you have the constant parameters, another one where the value of y, y naught these are not provided at t equals 0, but at some other value. Then by changing the scale of t, I can bring some new parameter and I can try to find out the solution by using the condition of y bar 0 or y dash bar 0. So, just let us see this thing. We are obtaining the solution as I described earlier. Just for your simplicity, you can go through this. That is the reason I am showing this thing. So, y bar tau you are obtaining from here using the shifting property. You are writing it to power s cube like this, and simply I can find out the solution of this. So, that you can obtain y t equals e power 1 minus t into t minus 1 whole square plus 1 is the solution. Now, see this problem. Solve t y double dash plus y dash plus 4 t y equals 0 with y 0 equals 3 and y dash 0 equals 1. Please note that here now the parameters are not constant of y double dash, y dash or y. They are function of t only. In earlier problems, whatever we did, the coefficients of y double dash or y dash or y were constant. Now, we are taking the parameter values as the coefficients as a function of t, that is t y double dash plus y dash plus 4 t y equals 0. Let us see the solution process for this type of problem. So, what is happening here? If I take Laplace transform of the given function, it will be Laplace transform of t y double dash plus Laplace transform of y dash plus 4 into Laplace transform of t y equals 0. What is Laplace transform of t y dash or what is Laplace transform of t y? Laplace transform of y dash we know it. What is your Laplace transform of t y dash? Usually I am just saying t y dash, I can write it as minus from the property minus d d s of Laplace transform of y double dash. I can write down this thing minus d d s of Laplace transform of y double dash. Similarly, if I want to take Laplace transform of t y, Laplace transform of t y will be minus d d s of Laplace transform of y in this case. So, using this property, now I can get back to my original thing. So, please note this, Laplace transform of t y double dash is minus d d s of Laplace transform of y double dash. Laplace transform of t y, I can write it as using the property minus d d s of Laplace transform of y. So, that now this using these two things, this I can bring it like this minus d d s of s square Laplace transform of y dash, I know it, s square Laplace transform of y minus s y naught minus y dash 0 plus Laplace transform of y dash, this is nothing but s into Laplace transform of y minus y 0 and 4 in plus 4 into Laplace transform of t y is minus d d s of this thing. So, basically it is minus d d s of Laplace transform of y, Laplace transform of y, this is equals to 0. So, once I am getting it from here, I can substitute the value of y 0, y dash 0 everywhere. So, I will obtain minus d d s of S square Laplace transform of y minus 3s using the given condition y 0 is equals to, it is given that y 0 equals 3 and y dash 0 equals 0. So, using these two conditions I will obtain s square minus Laplace transform of this minus 3s plus s into Laplace transform of y minus 3 minus 4 into dds of Laplace transform of y, this is equals 0. So, s square into this thing, I am getting this. Now, suppose I am assuming that, so up to this I hope it is fine. In the next step, I am assuming that say z equals Laplace transform of y. If s equals, then I can write down the earlier equation minus dds of s square z minus 3s plus s z minus 3 minus 4 into dz dds of Laplace transform of y. So, dz ds equals 0. So, from here once I am getting this s square dds of this and like this way. So, now you can form from here dz ds, dds you can make it. If you make dds over here, you will obtain minus s square plus 4 into dz ds minus sz equals 0. This dds I am just evaluating, dds of s square z minus 3s I am combining with minus 4z into this and I am getting this one, or this I can write down dz by z plus s into ds by s square plus 4, this is equals 0. So, effectively what is happening whenever you are having this log, you are having this t into y double dash or t y or say t y dash, then effectively you are not getting any algebraic equation, but you are going back to some again simplified ODE only. Please note this change again here, because in this particular process whenever I am starting this thing, then usually by using the Laplace transform I should get back some algebraic equation. But instead of getting the algebraic equation, it is again converting it into much simpler ordinary differential equation in terms of other variable like this dz by z plus s into ds by s square plus 4, which is equals to 0. And the solution of this usually you can write down, that is log z plus half into log of s square plus 4, this is equals log of c, because here I am using integrating on both side and some arbitrary constant I am choosing over here, log c I am choosing here. So, that log of z into root over s square plus 4, this is equals log of c. And so, what is happening? I am obtaining this equation, so that I can write down after this my z is nothing but Laplace transform of y, and this equals from the earlier you can write down z equals root over c by s square plus 4. Z equals Laplace transform of y, which is equals to c by s square plus 4. So, that y equals, you can write down the constant c into Laplace inverse of 1 by s square plus 4. And this value is nothing but the, if you remember this, this will be 1 by root over s square plus 4, because if root is not there it will be simply sign. So, Laplace transform of, if you remember j 0 to t, Laplace transform of j 0 to t is nothing but 1 by root over s square plus 4. So, here if you see Laplace transform of j 0 to t, this is equals 1 by s square plus 4. So, that this value will now become 1 by this is equals to c into j0 to t. So, what is the solution is coming now? Y equals c into j0 to t. Now, it is given that y0 is 3 is given to us at t equals 0, and we also know j0 at 0 this is equals 1. So, that you are obtaining 3 equals c j0 0, and so you are obtaining 3 equals c. So, your solution becomes 3 into j0 to t. So, you see in this case it is little complex that we are not directly obtaining any algebraic equation, but we are obtaining one ordinary differential equation again, although we have substituted the Laplace transform, and by finding the solution of the ODE only, again you are getting z equals Ly, and from there you are finding the solution. Let us see it once more, because this is little bit other type of problem. So, you are having the Laplace transform of t y double dash plus Laplace transform of y dash plus 4 Laplace transform of t y, this is equals to 0. So, as I told you, Laplace transform of t y double dash is nothing but the minus dds of Laplace transform of y double dash. So, that here minus dds of Laplace transform of y double dash, and I know Laplace transform of y double dash, I am substituting this value, plus Laplace transform of y dash, I know it, s into Laplace transform of y minus y0. Again Laplace transform of t y is minus dds of Laplace transform of y. So, please note these things. So, that minus dds, so it will become minus 4 into dds of Laplace transform of y. So, now substituting the value of y0, y dash 0, I am obtaining this, and if I substitute z equals Laplace transform of y, then I will obtain an equation like this, z equals Laplace transform of y. So, that z will be a function of s afterwards. So, minus dds of this will come. From here I am getting one ordinary differential equation. Please see it. This is an ordinary differential equation, not an algebraic equation, which initially we told whenever I will take one ODE, then using Laplace transform I will convert it into some algebraic equation. But when you have the terms like this, t y double dash, t y dash, t y like that, then the ODE again is converted into, after taking Laplace transform, ODE is converted into first order ODE, one order is being reduced in this case. Please note this one. One order has been reduced on this, and I can find out what is the solution of this. dz by z plus s by s square plus 4 ds is 0. I can write down. The solution is very easy, log z plus this. So, that log of z into root over s square plus 4 equals log c, and z I can obtain as Laplace transform of y, and which is equals to c by root over s square plus 4. So, from here y will be c into Laplace inverse of 1 by root over s square plus 4, and j0 to t is the function for whose Laplace transform is 1 by root over s square plus 4, and j0 is the 0th order Bessel function. So, j0 to t will come y equals c into g. Now, I have to only find the value of the constant arbitrary constant c. For that I am using the y0 equals 3, this one, c equals c into j0 0, j0 0 is 1. So, that c equals 1, and therefore, I obtain the solution as y equals 3 into j0 to t. So, please see the variation here. Whenever I have the terms like t y double dash, t y dash or t y like that, the ODE second order ODE will be converted into one first order ODE. That is by using Laplace transform. In this case, we are not converting it into the original algebraic equation, but it is converted into one first order ODE. We are finding the inverse, we are finding the solution of the first order ODE, and then taking inverse we are obtaining the solution. In the next lecture, we will take one more example on this, so that you can understand it in much better way.